Today we're going to talk about strong acids, strong bases, and finding the Ka for weak acids. So strong acids completely react with water to give hydronium. So we have a strong acid, either a gas or a liquid, plus water, pure liquid. So when I'm talking about the liquid for the acid, it's an aqueous solution, aka it's mixed with water. And then it goes to hydronium, aqueous solution, plus our conjugate base. And I'll write in either gas or aqueous solution. So when we write out our K, we get hydronium with the base all over our acid, our strong acid. Now normally our strong acid is represented by hydronium, but for this case we're going to start separating them. Now let's talk about what are strong acids. Here's a list of strong acids. 1. The hydrohalic acids, hydrochloric acid, hydrobromic acid, hydroiodic acid. Also, oxoacids. They are the number of oxygen atoms that exceed the number of ionizable protons by 2 or more. So, nitric acid, sulfuric acid, perchloric acid. So let's do an example of how we form an oxoacids. So let's take a look at sulfuric acid. Sulfuric acid has 4 oxygens minus the 2 hydrogens it has, and we get a number of 2. So because it follows the definition of an oxoacid, that means it's going to be an oxoacid and it's possibly a strong acid. Alright, so let's do a little bit of a problem. So what is the pH of 4.55 times 10 to the minus 3 molar of HNO3? So the first thing we need to do is we need to figure out, is this a strong or weak acid? Well, because we know that nitric acid is a oxoacid, that means it is a strong acid. Now we're going to first make a balanced equation, mixing it with water, just so you can see that it's in fact an acid. Form nitrate. And hydronium. Now the reason why we do this is because we need to figure out a balanced reaction. So what we know is we have 4.55 times 10 to the minus 3 nitric acid, but we're going to find the pH of that strong acid. So we know because we have a strong acid, it would equal to our hydronium. And we have a 1-to-1 mole relationship with this. So we're going to take our 4.55 times 10 to the minus 3 moles over 1 liter. And I just want to make sure you guys know to show the molar change for this, because it's going to come important when I show you another example. And we get 4.55 times 10 to the minus 3 moles of now the hydronium. So the second part is now we're going to find the pH using the negative log of hydronium. We're going to plug that in, and we're going to get 2.342. Now why have 3 significant figures after the pH? Because we had 3 significant figures as a full number for the molarity. Now let's take a look at strong bases. So a strong base is a base mixed with water to form a conjugate acid and hydroxide. Our list of strong bases are M2O or MOH, where the M is our group 1 metals like lithium, sodium, potassium, rubidium, and cesium. Then our next strong bases are MO or M hydroxide 2, where our metal groups are group 2 metals, calcium, strontium, and barium. Please note with that 2 for the hydroxides, it's going to make a difference on our balancing. So I'm going to show you an example of this. So what is the pH of a 0.01 molar calcium hydroxide 2 solution? So the first thing we're going to do is we're going to create a balance equation. So calcium hydroxide, we're going to mix it with water, and we're going to form calcium 2 plus 2 OH minus plus some more water. What happens is this water actually breaks apart right here, and what we're really looking at is the ions here. So number 2, now we're going to take our molarity and we're going to convert it into hydroxides. So 0.1010 molar times moles of the calcium hydroxide, which we have 1 of, but we have 2 moles of that hydroxide. So that's going to give us 0.020 molarity of that hydroxide. Now from there, we can find the pOH. So we're going to take the negative log of that OH negative, and we're going to get 1.70. Now, why do I have 2 sig figs after the decimal point? It's because I have 2 sig figs in my molarity. Next step, we're trying to find the pH. So we're going to find pH is equal to 14 minus pOH, which gives us 12.30. Again, you need to have 2 significant figures after the decimal point, and this is our answer. So make sure you watch out for the 2 moles of hydroxide that might pop up. For the acids, it's never really going to show up something like that, but just in case, just make sure you do a conversion. So we're given this question. We have 1.35 moles of sodium hydroxide, and it's dissolved in 250 milliliters of water. What is the pH of the resulting solution? Well, first, let's start making a molarity. So if we have 1.35 milligrams, we're going to convert that into grams, and then we're going to convert that into moles. And sodium hydroxide has a molecular weight of 40.01, and we get 3.37 times 10 to the minus 5 moles. Now, because we're looking for molarity, we're going to divide that by the volume, and we're going to make sure it's converted into liters. So we actually have 0.250 liters. So our molarity is 1.35 times 10 to the minus 4th molarity of NaOH. Now the second part we're going to do is create a balance equation. So we have NaOH forms with water. We know we're going to get sodium plus hydroxide plus some excess water that gets formed. And because it's a 1-to-1 ratio, we know that this is also hydroxide. So let's find the pOH. So we're going to find the negative log of that OH minus, and we get 3.870. Again, we have 3 sig figs. You need to have 3 sig figs after the decimal point. Now to find the pH is equal to the pOH. It's 14 minus the pOH, which gives us 10.130. And again, we need to have 3 sig figs after the decimal point. So our 6 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, perchlorate, nitric acid, and sulfuric acid. So there are 6 strong acids, and it's just easier to remember these 6 strong acids. Now let's talk about acid dissociation. Acid dissociation, so we would write it as, acid dissociation is HA plus water forms A negative plus hydronium, and acid dissociation is represented by the equilibrium constant of acid. That A represents the acid dissociation constant, and we get A negative hydronium all over the acid. So as Ka increases, our acid strength will increase. So when our Ka increases, our acid strength increases as well. So with strong acids, the reaction goes to completion, so our Ka is greater than 10 to the third. While for our weaker acids, our Ka is going to be less than 10 to the third. So remember, as Ka increases, the acid strength increases. And you can see this on page 781 in table 18.2. So let's do an example. So here we have acetic acid mixed with water to form acetate and hydronium. What is its Ka? And we get this expression. Now, let's say if we actually want to find out, well, what is the number of Ka? Well, let's do an example. I'm going to do sample problem 18.7 on page 790. Alright, so the question is, phenylacetic acid, simplified as HPAC, builds up in the blood of a person with phenylketonuria and is an inherited disorder that, if untreated, causes mental retardation and death. A study of the acid shows that the pH of 0.12 molar of HPAC is 2.62. What is the Ka? So the first thing we have is 0.12 molar of our HPAC, which is our acid, which is weak, and it has a pH of 2.62. And we're looking to find the Ka. Now, to find the Ka, we definitely need the molarity of the acid and the pH. If we don't have either or, we won't be able to find the Ka. Now, the first thing you want to do is write the dissociation equation and the Ka expression. So step 1 is writing out the dissociation equation, which is HPAC plus water. Remember, this water is in liquid form, goes into PAC negative, so that's going to be our conjugative base, plus hydronium. Now, the second part, which I asked you to, is find the Ka expression. So we're looking at Ka is equal to our hydronium, our conjugative base, all over our acid. Now, the second step we want to do is set up a reaction table. So this is how you'll set up the table. You will have your dissociation equation right up here, an initial, a change, and your equilibrium. Now, we know that our initial is, we start with 0.12 molar of HPAC For water, nothing is initial, nothing changes, and nothing is in equilibrium because it was not in our Ka expression. For our hydronium and our conjugative base, we don't know anything about the initial. Now the change, because we are changing, so our change for the acid for HPAC is going to be minus X because a little bit breaks up or disappears. For hydronium, we're going to have some that here as well as the conjugative base. So then we bring down what we have, 0.112 minus X plus X plus X. I want you to know that X is equal to the HPAC dissociation, which is equal to our hydronium from HPAC, which is equal to our PAC, or our conjugate base. Now for the next step, we're going to find the molarity of hydronium. So what we know is we have a pH of 2.62. So because our HPAC is equal to our H3O plus from HPAC, what we're going to call it, we're going to find the HO3. So we got 10 to the minus 2.62. So that's going to give us 2.4 times 10 to the minus 3 molar. Don't forget sig figs, because we have 2 after the decimal, we need 2 for the number for our molarity. Now the next thing we're going to do is we're going to make some assumptions. Well, first I'm going to figure out, well, can I use this H3O plus? So the first assumption I made was that my H3O plus is going to be greater than my H3O plus from water. So if we look at the number 2.4 times 10 to the minus 3, it is definitely greater than 1.00 times 10 to the minus 14th. So this assumption is correct, and we can make it. Now, the next assumption is that the HPAC is a weak acid, so we're going to assume the HPAC of 0.12 molar minus X is going to be equal to 0.12 molar. So this is our first assumption. Our second, we're stating again our HPAC, which is equal to 0.12 minus X, is going to be somewhat equal to 0.12. And we're going to double check these assumptions again. And this should be molar. So now that we have constituted everything, let's plug it into the Ka. Alright, so since we know that HO3 positive is 2.4 times 10 to the minus 3 molar, and that the PAC, the conjugative base, is also the same number, we're just going to square that. And that our HPAC is 0.12. When we calculate this, our Ka gives us 4.8 times 10 to the minus 5 molar. So this is what we get. So now I'm going to check for the assumptions. And what we do is the 5% assumption to make sure it's justified. So first, we're going to find for the hydronium of actual water, we're going to take what we know of water, which is 0.00 times, it's 1.00 times 10 to the minus 14th, all over what we actually used, which was 2.4 times 10 to the minus 3. And we're going to times that by 100, and we get a number that's 4 times 10 to the minus third percent. This is definitely less than 5%, so it is valid. Our second assumption is for HPAC, for dissociation, and we're going to take our molarity that we found all over the molarity of what we started with, times it by 100, and we get 2.0%, which again is less than 5%, so we are justified. Remember, we're using the 5% rule, so if it's less than 5%, it is going to be valid. Now let's take a look at another type of equation. This time we're looking for the pH. So let's take a look. Alright, so what is the pH of 0.25 molar of acetic acid solution, and the Ka is 1.8 times 10 to the minus 5 molar. Alright, so we're looking for the pH. Last time we were looking for the Ka. So for the first thing you need to do is find the dissociation equation and the Ka expression, which I have written out here. So here is the dissociation equation, and here is the Ka expression. Here I'm writing out what my X value will be for when I set up the reaction table. Next step, setting up the reaction table. Alright, so here's my reaction table. So what we know first is our initial. So what did we start with? We start with 0.25 molar of acetic acid. Water is not involved in this because it's not part of our Ka expression. We don't know the molarity of our acetate or our hydronium. What changes is we are getting rid of the acetic acid and we are forming acetate and hydroxide. So when we write out our equilibrium, we have 0.25 minus X, and plus X. Now, what we're going to do is build what we have. So what we have so far is Ka is equal to X for the hydronium, X for the acetate, all over our acetic acid, 0.25 minus X. Because we're going to assume this is a weak acid, which it is, I'm going to take out the minus X. So usually if it's a weak acid, we can do this. Now we know that our Ka is equal to 1.8 times 10 to the minus 5 molar. So when we do a little bit of math, we get X squared is equal to 4.5 times 10 to the minus 6, and our X is equal to 0.0021 molar. Don't forget, you need to have two significant figures because you have two significant figures here. Now, we're going to say this X is our H3O plus because we're looking for the pH. It's also H3O plus. It's also our conjugated base. So let's solve for pH. So pH is going to equal to the negative log of our hydronium, which is 0.0021, and we get 2.67. The sig figs is 2 sig figs, so we need 2 sig figs after the decimal point. Now we're going to check to make sure our assumption that it is a weak acid is correct. So I'm going to take 5% and divide it by 100, and then I'm going to multiply it by the concentration to get 0.0125. Because this number is so much bigger than 0.00212, which is the number I got, I know that this was valid because this is my 5% error and this is the number I actually received. Another way of looking at this is to take your 0.00212, divide it by 0.25, which you started with, times 100, and it gives me 0.84%, which again is less than 5%, so it is valid. There's two ways of looking at this. It is up to you on how you want to look at it. Alright, so that is it for this part of the section. So this is the assignment for you. So you have reading Chapter 18, sections 4 through 5, and the problems of Chapter 18 in the back of the chapter, 23, 41, 65, 73, 63, 71, 86, 88, 90, and 92.